Welcome to this problem walkthrough. Today, we'll be tackling LeetCode problem number 2205, titled Cannot Provide Actual LeetCode Problem Details. In this session, we'll explore various approaches to solve this problem effectively, breaking it down step by step. Let's dive in. Regrettably, we are unable to provide a detailed explanation for LeetCode problem number 2205 titled Cannot Provide Actual LeetCode Problem Details. The absence of problem-specific information, including the description, input-output format, examples, and constraints, makes it impossible to generate the requested content. If additional information about the problem becomes available in the future, we will revisit and provide a comprehensive breakdown. When tackling LeetCode problem number 2205, we begin by exploring various potential approaches. First, it's important to consider the brute force strategy, which involves systematically checking all possible combinations or permutations of the input to find a solution. This approach is often our starting point because it provides a clear baseline for correctness and allows us to understand the underlying structure of the problem. However, brute force methods tend to be computationally expensive, often with time complexities of n squared, or worse. While this makes them impractical for large inputs, they are valuable for establishing a foundation before moving on to more efficient techniques. Brute force, while straightforward, has limitations due to its inefficiency with larger input sizes. This is where optimized approaches come into play. By leveraging data structures such as hash maps, heaps, or trees, we can significantly reduce redundant computations. For example, if the task involves searching or aggregating data, hash maps can offer average time complexity for lookups, making them highly effective. Of course, these optimized methods come with trade-offs, such as increased memory usage, which must be carefully considered. Additionally, for problems with recursive or overlapping substructures, techniques like dynamic programming or divide and conquer can break the problem into smaller, more manageable pieces. These methods allow us to improve time complexity dramatically, often converting exponential runtimes into polynomial ones. While highly efficient, these strategies require a deeper understanding of the problem's recursive nature and careful formulation of base cases, states, and transitions. The choice of strategy for solving problem number 2205 ultimately depends on the specific constraints, input size, and desired output. A general roadmap involves starting with a brute force solution to verify correctness and gain insights into the problem. From there, we look for patterns or redundancies that can be optimized using data structures or algorithms. Finally, we consider advanced techniques such as binary search, sliding windows, or dynamic programming, depending on the requirements. The key to success often lies in identifying an aha moment, a property or pattern in the problem that simplifies its complexity. For instance, recognizing that a greedy approach can replace exhaustive search can lead to significant improvements in efficiency and scalability. The chosen strategy is designed to balance correctness, efficiency, and scalability. Starting with a brute force approach ensures we have a working solution as a foundation. From there, optimization reduces runtime and memory usage, and advanced techniques help us handle more complex scenarios. This layered methodology not only deepens our understanding of the problem but also makes debugging and scaling easier. Each approach has its trade-offs. Brute force guarantees correctness but struggles with large inputs, optimized methods improve performance but may be harder to implement, and advanced techniques are highly efficient but often require careful analysis and may not generalize well. By iteratively refining the solution, we can adapt to both small-scale and large-scale inputs, confident in our ability to meet the problem's demands. To approach any algorithm problem effectively, the first step is to fully understand the problem statement. This means carefully analyzing the requirements, constraints, and any potential edge cases. For instance, you need to determine the structure of the input, whether it's an array, string, graph, or something else, and identify the desired output, such as a single value, a modified data structure, or a Boolean result. If the problem involves finding patterns or subsets, think about applicable techniques, like sorting, hashing, or the sliding window approach. Next, selecting the right data structure is crucial because it directly impacts the time and space complexity of your solution. For example, a hash map is great for quick lookups, while a heap is ideal for dynamic minimum or maximum extraction. If frequent insertions and deletions are required, a linked list or deque might be more efficient than an array. Choosing the right tools here sets the foundation for an optimal solution. Once you've laid the groundwork, the next step is to develop the core logic of your solution. Break the problem into smaller, manageable steps. Start by parsing the input data, such as iterating through an array or splitting a string. Then, apply the algorithmic technique you've chosen, like sliding window, dynamic programming, or binary search. As you proceed, use the selected data structure to update intermediate results efficiently. For instance, in a sliding window approach, you would initialize 2 pointers to define the window, adjust the window size based on the problem's conditions, and maintain the current state in an auxiliary structure, such as a hash map. After building an initial solution, focus on optimizing it. Look for inefficiencies or redundant calculations. Techniques like memoization or pre-computation can help streamline the process. In a dynamic programming problem, for example, storing solutions to overlapping subproblems ensures you don't repeat work unnecessarily. Handling edge cases is a vital part of designing a robust algorithm. These can include scenarios like empty inputs, maximum or minimum input sizes, and special cases such as duplicates, negative numbers, or cycles. Identifying these edge cases early and adding specific checks in your code ensures your solution remains reliable under all conditions. After accounting for edge cases, it's time to rigorously test your solution. Start with simple base cases to confirm your logic works as expected. Then, test edge cases to ensure your code handles them gracefully. Finally, use large datasets to evaluate performance and verify that your solution meets the problem's constraints. This comprehensive testing process helps you identify any remaining issues and ensures your algorithm is both accurate and efficient. Effective problem solving often involves iterative refinement. Starting with a brute force approach can help you understand the problem better, and from there, you can refine your solution step by step. It's also important to recognize the trade-off between space and time. For example, using a hash map to store intermediate results may increase space usage but significantly reduce computation time. Another key insight is recognizing patterns. Many problems follow common patterns like sliding window, prefix sums, or 2 pointers. Identifying these patterns early allows you to apply proven strategies, saving time and effort. Additionally, the choice of data structures plays a significant role. A hash map is excellent for quick lookups and frequency counting, while a heap is perfect for dynamically finding minimum or maximum values. For sliding window problems, a deque enables efficient insertions and deletions on both ends. And when working with graphs, you can choose between adjacency lists or matrices depending on the graph's density. Mastering key algorithmic operations can further enhance your problem-solving efficiency. For example, the sliding window technique allows you to efficiently manage subarrays or substrings by maintaining a dynamic window of relevant elements. Hashing enables constant time lookups, making it ideal for problems involving uniqueness or frequency tracking. Binary search is another powerful tool, especially for sorted data or when searching for thresholds. To optimize your solutions, aim to minimize unnecessary loops, particularly nested ones. Auxiliary data structures can help track intermediate states more efficiently. Memoization is invaluable for storing results of overlapping subproblems, which avoids redundant calculations. Pre-computation is another useful strategy. For instance, calculating prefix sums or factorials in advance can significantly speed up queries. By combining these techniques, you can craft solutions that are both efficient and elegant. The provided Python implementation is a template for solving LeetCode problem number 2205. Since the exact problem statement is unavailable, the solve method includes placeholder logic that simply returns the input data. This demonstrates the structure of a typical solution class on LeetCode. To adapt this template, replace the logic inside the solve method with the actual algorithm required to solve the problem. But if __name__ equals __main__colon block is included to allow testing the solution independently, with an example input provided. Replace the data variable with the specific problem input format and test the implementation accordingly. This is the Java implementation of the given Python logic. The solve method serves as a placeholder for the actual solution, and in this example, it simply returns the input data as is. The Java implementation mirrors the Python approach but includes type declarations and utilizes Java-specific collections such as list and arrays. The main method demonstrates example usage, making the program executable as a standalone Java application. To begin, we have example 1 with a simple input consisting of the list 1, 2, 3, 4, 5. The method solve is called, and the input data is passed as the parameter. Since the placeholder solution doesn't perform any transformations, the input remains unchanged during processing. The method then returns the exact same list 1, 2, 3, 4, 5, which is printed as the final result. This demonstrates how the method currently behaves when given a straightforward input with consecutive integers. Now, looking at example 2, we test the method with an empty input list. The solve method is called with this empty list, and since the solution is still just a pass-through implementation, no operations are performed on the data. The method simply returns the same empty list as the output. This result is printed as the final output. This example confirms that the placeholder solution handles empty inputs correctly by returning them unchanged. Next, in example 3, we have a more complex input that includes mixed data types, a string, an integer, a floating point number, and another string, represented as apple, 42, 3.14, banana. The solve method is called with this input, and again, no modifications are made to the data. The method directly returns the same list as the output, which is then printed as apple, 42, 3.14, banana. These examples collectively demonstrate that the current implementation simply returns the input as is, regardless of its contents. In a real-world scenario, the solve method would include logic to process the input meaningfully and produce a computed result. In this section, we start by analyzing the time complexity of the given code. The implementation is quite simple. It involves directly returning the input data without any additional operations. Accessing the input data is an O1 operation since it only involves referencing the argument passed to the method. Similarly, returning the data as is also O1, because no extra processing, iteration, or copying is performed. Therefore, the overall time complexity for this implementation is O1, which is constant time. However, this is only true for the current placeholder logic. If the problem requires more complex operations, such as iterating over the input, performing a sort, or using recursive calculations, the time complexity will scale based on the size of the input, denoted as n. For instance, a single iteration over the input would result in O(n), sorting the data would give us O(n** log n, and nested iterations could lead to O(n²). The actual complexity will depend on the specific operations required by the problem. Now let's turn to the space complexity of the implementation. With the current placeholder logic, the analysis is straightforward. The input data is passed as an argument to the method, meaning no additional memory is consumed beyond the input itself. Similarly, since the method returns a reference to the same input object without creating a copy or modifying it, no extra space is used for the output. Moreover, there are no auxiliary data structures or variables being created, nor is there recursion involved, which means no additional memory is used. Therefore, the space complexity for this implementation is O1, representing constant space usage. However, if the actual solution involves additional data structures, such as arrays for intermediate storage or hash maps to store results, the space complexity would increase. For example, storing results in a hash map would require O(n) space, where n is the number of elements in the input. Similarly, recursive solutions would require space proportional to the maximum depth of recursion. The specifics of the problem would dictate how memory usage scales. Finally, let's compare the current placeholder logic with potential real-world scenarios. As it stands, the implementation achieves both time and space complexities of O1, which is optimal since no computation beyond directly returning the input takes place. However, in realistic problem solving, a brute force approach, such as iterating over all elements and performing nested operations, could lead to significantly higher time complexities, such as O(n²) or worse. Optimized solutions aim to reduce these inefficiencies by leveraging techniques like sorting, dynamic programming, or divide and conquer, which often achieve better results, such as O(n** log n, for sorting or O(n) for a linear scan. Ultimately, while this placeholder logic represents the simplest case with minimal complexity, the actual solution for LeetCode problem number 2205 will depend entirely on the algorithm implemented to address the problem's requirements. A thorough breakdown of the operations involved will be essential to accurately assess the time and space complexity of the real solution. When tackling coding problems, it's essential to avoid common mistakes that can derail your solution. For example, not considering edge cases is a frequent issue. Think about scenarios like empty inputs, single-element arrays, or values at the maximum constraint. These situations often expose hidden flaws in your code, so make sure to test for them explicitly. Another pitfall is relying on brute force solutions without analyzing the problem's constraints. This often leads to inefficiencies, such as time limit exceeded errors, especially when the input size is large. Instead, take a moment to assess the problem's complexity requirements before diving into implementation. Additionally, selecting the wrong data structure can severely impact performance. For instance, using an array when a hash map or heap is more appropriate can unnecessarily increase time complexity. Always align your choice of data structure with the operations the problem demands, like searching, inserting, or sorting. Handling duplicates incorrectly is another common oversight. Problems often specify how duplicates should be treated, so read the problem statement carefully to avoid errors. Lastly, misinterpreting constraints or requirements, such as confusing non-decreasing order with strictly increasing, can lead to incorrect solutions. Always take the time to clarify these nuances before you start coding. Now, let's discuss some key insights for interviews. Recognizing common problem-solving patterns, such as sliding windows, two-pointers, dynamic programming, or graph traversal, can give you a significant advantage. Many interview problems are based on these patterns, so identifying them early can help you formulate an efficient solution faster. It's also important to weigh trade-offs between time and space complexity. For example, some problems allow you to reduce runtime by using additional memory, while others might require optimizing for space efficiency even at the cost of a slightly slower runtime. During interviews, communicating your thought process is just as important as solving the problem itself. Even if you're unsure of the solution, explaining your approach shows your problem-solving skills and helps the interviewer follow your reasoning. Lastly, adopt a habit of testing your code as you develop it. Writing small, targeted test cases during implementation allows you to catch bugs early and saves you the frustration of debugging large, complex test cases later. Certain related problems can help you build a deeper understanding of common techniques and strategies. For instance, LeetCode 1.2 sum is a foundational problem that demonstrates the efficient use of hash maps for lookups. LeetCode 15.3 sum introduces sorting and two-pointer techniques, which help in solving problems with specific constraints efficiently. LeetCode 149, max points on a line emphasizes mathematical insights and hash map usage, pushing you to think creatively about representing relationships between points. Finally, LeetCode 560, subarray sum equals k combines prefix sums and hash maps to achieve optimal performance. In addition to understanding these problems, it's useful to explore alternative approaches. Brute force, while inefficient, can be a great way to validate your understanding before optimizing. Optimized data structures, like hash maps, heaps, or segment trees, often reduce time complexity significantly. For example, using a heap to find the kth largest element is faster than sorting the entire array. Additionally, divide and conquer strategies are particularly effective for problems like maximum subarray, where breaking the problem into smaller parts and combining results leads to an elegant solution. Sliding window and two-pointer techniques are particularly powerful for problems involving subarrays or substrings. These methods can drastically improve efficiency by reducing time complexity from O(n) squared to O(n). The key idea is to avoid redundant computations and instead focus only on the elements that need to be processed at any given time. For instance, a sliding window dynamically adjusts to include or exclude elements as needed, while two pointers systematically move through the array to maintain a valid state. These techniques are versatile and widely applicable, making them essential tools in your problem-solving toolkit. Great job! Today, we explored problem number 2205, breaking it down into manageable steps. Remember the importance of analyzing constraints, handling edge cases, and writing efficient code. If you enjoyed this walkthrough, make sure to like, share, and subscribe for more content like this. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!